Good evening, everyone. Can you hear me? Is it okay? Can you hear me? I appreciate that indeed that you stayed until the late presentation, and I do realize that I'm the last person standing between you and reception, I guess, beer. So I'll try to keep it short. I work at Pivotal. I'm an engineer there where I focus on big data, distributed systems. I'm privileged to spend enough time on working on open source project. I'm Apache committer and PMC member for Apache Calcite project. Today I'm going to talk about two interesting trends. One has happened in the last decade, the last 10 years. This is the NoSQL and big data. The other one is the implementation of SQL interfaces for various NoSQL data systems, which seems to be happening. It's a big theme in the last year and a half. And this is a quote I found from Martin Fowler from 2012, where he predicts that if ever SQL gets implemented on top of established NoSQL, this at least would generate plenty of arguments. And I believe this talk is going to be one of those arguments. So, little bit of context. The big data and NoSQL Big Bang. This is a landscape of big data technologies for the last year. You see, actually, according to some sources, we have over 150 commercially supported NoSQL and big data systems out there. So what actually explains this explosion, considering that for decades we've been happy, or some people have been happy with relational databases? It's difficult to judge by the name of those projects, NoSQL, on actually those trends. NoSQL or big data, they really don't provide any prescriptive definitions. But if you think of them more like a movement and try to understand what are the driving forces behind them, I think this helps to position them and to understand why they're so vibrant and what makes them tick. On the first place, I think there's some consensus about this. One of the main driving forces behind those technologies and the boom of those technologies is the boom of internet itself. The fact that explosion of web, mobile technologies, Internet of Things, practically any device now, even smaller one, is a source of information and generate information. And this in turn generates three main challenges. This is how to handle the volume of data, the velocity of data, and the variety of all these data sources. So, Internet is the cause for these technologies, or for the demand for those challenges. On the other hand, it is actually the solution as well. In order to handle, to scale, to provide technologies that can handle and address those challenges, you are going to use, again, distributed systems. And in turn, using distributed systems for resolving those challenges means that some of the already presumed technologies and guarantees that relational databases provide, like ACID or two-phase commits, would be challenged and has to be addressed in different way. It's known, for example, that the two-phase commit would hang in certain cases in failure distributed systems. So all new class of approaches, for example, the consistency and availability in case of partitioning of distributed system. This is the CAP or theorem are meant to deal, and this is part of the distributed system and many of the technologies that implements this. Paxos, on the other hand, and as I mentioned, the two-phase commit is not really a reliable approach to ensure consistency within the distributed environment. So all class of consensus-based, quorum-based systems like Paxos have emerged, and many of the NoSQL systems actually are based on those type of technologies. Another not that popular, but I think very important driving force is the so-called relational or object relational impedance mismatch, which relational database, I'm not sure many of you maybe have done some application development. They know that for some class of applications, you just need to persist your application state, which in my case very often is object-based state, into a relational database. For this, you would need some sort of ORM technologies, which is unnecessary for many use cases, as I mentioned. And this gave birth to technologies like Mongo or document-based data store. This actually is a huge group of technologies out there driven by this mismatch. Furthermore, different type of stores and demands like graph-based databases or full-text search, where the traditional representation of database models and strict, very often the role-based relational models, is not very appropriate to deal with. And There are many other factors, but I think those three kind of are powerful enough to explain why there is such a search of technologies out there. Last one I want to talk is the cloud computing race and wave itself. The possibilities to program the infrastructure, actually to automate this infrastructure, to have infrastructure on demand, is a main driver for eliminating the operational complexity and the cost. And there is another side effect of this, and this more architectural. There is this sub-movement, I would say, which is shift from integration to application type of databases. This is very popular into the microservices or type of data applications. So the idea is that if you have your application, instead of having a single data store as an application state for your distributed application, you rather have a dedicated application store for each application and have a well-defined protocol at application level between these applications, so the database is not shared among them. I hope those forces explain the reason why there is such a multitude of technologies out there. And I don't want to justify this or to dive further. The point is that there are out there a lot, and as I said, over 150 commercially supported one. And one of the interesting consequences of this is that almost any organization would end up with having at least few of those technologies deployed in their data infrastructure. So, interesting question raised: how they're going to integrate those technologies? This multitude of database that would usually they would have at least few data storage technologies dedicated to particularly good for particular type of use cases. And it was discussed today. I have observed so far two main trends that trying to provide this type of integration. And by the way, the integration of technologies is very big deal. Usually the standard ETL technologies and systems are trying to cope with this. That's not what I'm going to talk today. I'm really trying to talk about how an organization can provide a singular holistic view over the data that is spread across different data stores, which might be useful for certain use cases. Very often those are the analytical or maybe some data science type of use cases to train their data sets. So two main trends are emerging that are aiming to in my opinion, to converge and to provide more unified view on the data system and data processing system. One is more functional based, it's unified programming model, and you can, today it was mentioned, there was a very nice presentation comparing the interfaces of Spark and Flink. You have noticed that they're very close, and actually they're not the only two that are very similar. Apex, Apache Crunch, Cascading, Apache Beam, they're all actually inspired by a common one paper from 2010, I think it's Flume Java, Google paper, as a type of API. And there is a trend now, at least that Spark, Flink, and Apex are implementing and converging at certain level under Apache Beam as a project. So this is example snippet of how Apache Beam looks as a notation. The second trend, and that's what I'm going to focus now today, is apparently a lot of the NoSQL vendors and big data vendors are starting to implement SQL interfaces for their data stores, or some sort of SQL-like interfaces for their backend data stores. And some statistics from the last couple of years for Hadoop shows that apparently majority of the tasks that are run on Hadoop nowadays are either Hive-based or SQL, some sort of SQL and Hadoop type of solutions out there. Also for Spark, there is a report from last year states that the most used production component is the Spark SQL within their system. So there is this, and I stated Google F1 paper actually has a quote there that any data system has to provide SQL interface, and I found this particularly important because a lot of the big data technologies are now in the open space are influenced from the Google papers. So there is this shift in ideas, and it's interesting movement and trend to observe. Apparently a lot of companies, I think it's worth it to try to reason what are the reason, what is the main driver for this movement, for this convergence. It seems like the desire, there is a lot of tools that know how to talk SQL out there within the organization. So it seems like SQL is a pretty easy way to integrate with those existing tools. So this is more like legacy reason. Secondary, and I think this is a more important one, is the relational model that stays under usually SQL engines, and this is the hot bits that we can talk about. We should talk about today, and I think this is important slide, although it doesn't seem very bright. I can argue that practically any useful data system out there, in one or another form, implements the set or back semantics. So operators like projection, filtering, if the system is more advanced at some sort of join or group by, would be present. So in order to provide some usefulness for the users, the system have to implement explicitly or implicitly those operators. So having this and acknowledging that this exists, and very often in order to implement a pipeline or query execution statement, you have to chain multiple operators like this. And when you start to play with this concept, you realize that practically this is the same relational algebra concept that are very common in the relational space. And there is a tools that are very good in optimizing some type of change, and those are the planners. And indeed, the relational expression optimizers are very desirable feature for many of the technologies, big data technologies. Simply, they're very difficult to implement. That's at least they were very difficult to implement until recently. Now there are at least a couple of open source technologies out there that provide some help and are useful to consider and try to use and leverage in order to provide this type of relational expressions and relational optimization within the existing big data systems. I'm proposing here, I mean, this is again just simple subset of possible way how you can integrate, how organizations are. I'm dealing with a lot of customers out there, so I have some first-hand experience with some big players in the field, and see and experience how they preserve and how they see the usefulness of the data, how they're trying to integrate their data. And it seems like the most common approach is this one. So this is standard federated database system approach. So you pick one database that allows you to implement connectors to external databases or the external data systems, NoSQL, and then you can provide kind of singular view on your system just via external tables, which are representation of the external NoSQL data systems. In this case, I have experienced with Apache Hawk, which is yet another tool derived from the Green Plum that we discussed today, again, which was derived from Postgres. It's MPP, shared nothing solution, which has very powerful. They actually share very similar optimizer, it's org optimizer inside. And what's more important, provides a Pxf Framework. This is a Java extension framework, which allows you to actually implement the plugins for external systems. So this is, I call it a N1N model, because the organization would use a singular SQL, usually Postgres, GDBC connection or ODBC, to talk with one MPP database, and via the extension mechanism would be able to see some portions of the NoSQL system itself outside. Second approach is far more interesting in my opinion, because it provides more autonomy for the NoSQL system themselves, is to implement a SQL adapter for each system in isolation. And for this purpose, there is a framework, very powerful framework out there called Apache Calcite. And as you can see, in this case, each of the NoSQL system would actually have its own SQL representation interface, its own optimization. The advantage of this is that you might be able to tune the optimizers for SQL optimizers and the relational algebra expression optimizers better to the particular specifics of the NoSQL system. And there is an interesting Jira ticket, the Jira issue that recently popped up, which is exploring the possibilities to bridge those two approaches. Just one slide about the federated database approach, how it looks like. So on the SQL standpoint, you're creating a table that looks like this, standard type. The interesting bit is that here you're providing location to your NoSQL data system where you want to wrap. And you have to implement three classes, which is the fragmenter, accessor, and the resolver. The purpose of the fragmenter is that if the NoSQL data store allows you to partition the data in streams that you can process in parallel, the role of the fragmenter is indeed to establish this partition. For each of the streams, or separate streams, in parallel, the accessor actually breaks them into a collection of rows, key value rows, and for each of these value rows, the resolver, the last component you have to implement, would convert it into column list which would match these interfaces. There is much more internals. You can pass analytics and stuff to configure the statistics in order to optimize help the optimizer to adjust according to this particular data store. And this is very powerful approach. If you, for example, already have Hadoop and Hawk-like system in your infrastructure, and you can just implement such type of plugins and wrap and provide holistic view of your backend system. The second approach, or the direct one, is to implement a SQL interface around your and leverage SQL optimizer around your NoSQL database. And for this, the Apache Calcite framework provides you query parser. This is SQL query parser, validator, optimizer. I think this is the most important bits here. As a bonus, you get the JDBC driver, which you can talk with the system. And one very important design decision about a Calcite is to stay out of the business of how data is stored and processed, which in turn makes it very useful to implement and wrap almost any existing data store out there. I think this is by design, and it's very powerful decision. And if you take a look about the various technologies out there that use in one another way Apache Calcite, you would see that most of the big play already using it inside. What I did, I'm working on Apache Geote adapter. The Apache Geote is in-memory data grid, yet another key value store, distributed hash, and I'm going to use some of the examples just as a reference to illustrate how it looks like. So, this, assuming that you decide to implement a SQL adapter using Apache Calcite for your backend data store, NoSQL data store, there are a couple of decisions you have to make, and they're very important regarding from one side, how much SQL completeness you are going to expose and compliant with the SQL standard. On the other hand, how much you're going to leverage the power of the NoSQL system you have. So the first thing is you have to decide how you're going to convert your data type from the existing NoSQL system, let's say this is key value store, or it could be even like some sort of graph representation, into a tabular format that is expected by Calcite. And Calcite has the standard metadata expected. It's the catalog, schema, which is collection of tables, table, which is collection of rows, and row is just a list of columns representing the relational data type. So this is important decision because let's say that you want to express some sort of a JSON or Java object which has hierarchy, and you have to flatter in some tabular format. You have to decide whether you're going to spend computation and a lot of serialization to achieve this, or you just can afford to implement only top level fields or some smartness and stuff. So it's up to you to decide what is it's a trade-off. So how much you're going to expose from your model as an opposite of the performance that you're going to gain or lose. And the second more important thing, and this is general principle for any distributed data system, is move the computation next to the data, not other way around. That means that if you, in the context of the SQL query, you would like to run the executions of this query next to the node where data is stored, rather than actually moving the data to some central node where this processing is happening and then moving it back and forth. In the context of Apache Calcite, you have two approaches to achieve this. The first one is simple. I call it simple. It just allows you to implement a very simple table interface with ability to push down the predicates. Predicates are operators, relational operators like filters and projections. That means that if you have select some fields from some table where something, it makes really sense these fields and the where clause, the conditions, to be pushed down to your NoSQL solution, and you pre-filter and pre-process and return back only the amount of data that is necessary for the system to process. I'm going to hurry up. This is an example how it looks, this simple scenario. You're connecting to, I'm not sure if it's visible, this JDBC adapt. This is the Apache Calcite JDBC protocol. So when you connect to JDBC via the Apache Calcite JDBC driver to your backend system, you have to provide a model in JSON format. The only thing that model contains is your entry point implementation of the schema factory. with some operands that are relevant for your backend systems. The role of this schema is usually one-liner of implementation, is to create a schema based on those operators operands that you have provided. The schema in turn depends on the mapping that you have decided to implement for your backend system, SQL system, and the relational stuff would create a list of tables. And the important thing is that you have to implement the column types within these tables. Then when a query comes, it would be passed through the scan parameter. So the from this book order usually would mean that it is going to try to extract this data set from your NoSQL database and convert it in the convert method, convert it into type that is compliant with the table definitions. The trick here is that in this simple implementation, you would get all data. So there is no any moving of the computation code to the data. Everything goes to the central processor and get processed there. There are two versions that you can optimize this computation. It's called that instead of scannable table, you can implement future scannable table or projected future scannable table, which allows you to push down the filters and projectors. But that's everything that you can do as an optimization. If you have a joins operators or group by operators, everything would happen central place on the client side. And the second approach that the Calcite provides you with is to implement your own relational rules and relational operators that would allow you to provide implementation much closer to the native NoSQL system. In this case, this is Apache Geode, and this is very fast going. So how it looks like. GDBC, this is everything in blue is the standard Apache Calcite framework. This is the bits that you have to implement in order to provide the adapter, and this is code generated by Calcite. So SQL query comes, it is passed to the parser. SQL is converted into a relational expression and tree. It goes through the planner, which performs some optimizations. Actually, while performing these optimizations, optimized tree is passed to the enumerable component, which is responsible to convert this logical plan into physical plan. And this is already the tricky part. In this process, actually, if you have implemented your own rules or operators, the enumerable components would consult those and would provide a well-tailored implementation. Actually, it uses the expression trees. This is concept from Link4j. I think this is something that comes from Microsoft. And this interpreter actually generates Java code that's optimized for this implementation, compiles it, and the GDBC query is executed. So that's the whole full, the complete line. And I'm going to skip this. Those are the internals of the, if you're going to implement your own rules and operators in Calcite, you would have to get acquainted with this. And this is the generic part. And if you see any of the implementations of the Calcite adapter out there, more or less implement and follow these steps here. And just, I would finish with the example. Let's say that you have these relational expressions. This is the relational operators that you would see. We have join of two tables, filter and project two of the fields. So the optimizer's role would be to convert and to push some of the operators closer to the data. So you see the projects, so to reduce the amount of data that moves upwards. So this is usually the logical part of the parser, of the optimizer. And this is the real example with the Apache Geode adapter that I've worked on. If you have this query, this is the logical plan. You see that you have no any optimization, the scan on the tables, then join is performed, then filter on this one of the fields, and projection extract two of the fields. If you use the simple scannable approach, which doesn't implement any rules, you would have some advantage, so that the planner would already reorder this operator in a way that would be executed much more efficiently. But still, most of the computation would happen on the client side where the GDBC or the SQL query is performed. If you move one step and you implement your own rules and have something that's much more tailored to your NoSQL data system, in this case, I have implemented Geode project, Geode filter board. There's also group by. You see that actually it uses those operators and it leverages practically a lot of those operators now executed on the NoSQL system itself. Still, you see that join is not implemented there. I'm working on this. That means that now this query practically would be converted into two subqueries run on the NoSQL system, and the result would be returned and be performed on the client side. But this is something that you can progress on. Typical GDBC, how we are going to use this Java standpoint. And I'm afraid I'm over time, so I'm sorry for this. Try to run through it.